All right, so here we're going to talk about section 1.4. Before we get into what 1.4 is all about, right, and why we're going to need it and use it, what we want to do is let's consider multiplying a matrix times a vector. Okay, it sounds like a weird thing, but it'll make sense when we get through this. Now, we're going to do what's called row by column. Now, what does that mean? Now, before we talk about it here, later on, we're going to be doing a matrix times another full blown matrix. We're going to do a matrix times a matrix. And that's when that term row by column is really going to make sense here. But it's kind of nice to get used to it now. Okay. But basically, what we're going to do is you're going to multiply the entries of the row, basically row one of the matrix, by the corresponding entries of the vector, and then you add the results. And then you basically repeat for each row. Okay. Now, if it was a full blown matrix, you would just repeat that for each column. So let me show you what I mean. So it's kind of weird at first. Once you get used to it, it's not bad. But think of it as, see, this is row one here, and then there's only one column in the vector, but that's it. So it's row by column. So what you're going to do is you're going to multiply the course. Let me write the whole thing out. So you're going to multiply the corresponding entries. Like, so first entry here, first entry here. So that's 3 times 5. And then the second entry here, second entry here. So that's 2 times 2. And then you add the results together, right? So there's 15 plus 4, so 19, right? So that would be the corresponding entry of the resulting, right? Then you just repeat for the next row by column, right? So here now it's 4 times 5, and then -1 times 2, and then you add the results together. So 4 times 5 would be 20, minus 2 would be 18, right? So So first off, realizing that a matrix, a full blown matrix times a vector is going to produce another vector, right? That's what it results in. But basically, think of it as it's row by column, and you just keep doing that. Okay, so it's kind of the same thing. If there's more of them, see, you would do row by column, row by column, row by column, right? And you just keep doing that all the way down. Okay. So even if it gets bigger here, like this matrix could get bigger. Okay, all right, so let's do it. And when you get good at these, you can just write out the answer. I don't care. You can even use a calculator. It'll understand this. I'll show you that in a second. But again, it's kind of the same thing. There's going to be some variables floating around at some point, so you got to know how to do it by hand as well. So don't just rely totally on the calculator. Um, but basically, again, row by this column here, right? So it's basically 3 times the 5, and then 2 times the 2, just like it was before. That's still 15 plus 4, it's still 19, right? And then take the next row by the column. So 4 times the 5, and then the -1 times the 2, add them together. So there's your 20 minus 2, still 18, right? The thing that's different with this example is now there's more rows, right? But the process is basically the same. It's -3, -3 times 5, and then the 2 times the 2, right? So -15 now plus the 4 would be -11. Okay. And if there were more rows here, you would just keep doing it. You just keep repeating, right? So this is a 2 by 2. This is a 3 by 2. You would just keep going. Okay. All right. Now, here's the thing. This would be great if we were in class, you'd be like, okay, so how do you guys think we would do this? And hopefully you kind of see, wait a minute, you're going to have a problem here, right? Just think about that. If you're going to try to do this row by this column, right? I mean, the 3 would go with the 5, and the 2 would go with the 2, and then who's the 1 going with? You can't do that, right? There isn't anything there. So you can't actually multiply these together. So this would be known as what's called undefined, right? There's no definition of how to do that, right? Um, so another way you can kind of look at this is notice, see how like this matrix here, this is a 2 by 2 matrix, and this vector is technically a 2 by 1, right? Then this is a 3 by 2, and this is a 2 by 1, right? This is a 2 by 3, and this is a 2 by 1, right? Vector. And the point here is basically in order for the multiplication to make sense, these would have to be the same, right? So if these are the same, then the matrix, well, matrix multiplication in general would make sense, but even matrix times a vector would make sense, right? Because think about it. The corresponding entries here has to match up with the corresponding entries here, here, and here, and here don't match up, right? That's why this is undefined. Okay. We'll talk more about it later because right now we're just talking about a matrix times a vector. But later on, it's going to be a matrix times any other matrix. Okay. And the general idea still works. If these are equal, then it makes sense. If these are the same, it makes sense. If these are different, it doesn't make sense. And also, it turns out that whatever this is, that's what the resulting will be, right? And whatever this is, that's the result. Whatever this is, that's the result. It's just that since these are vectors, these are all by one. That's why the resulting 2 by 1, 3 by 1. Wow, this one didn't even make sense. But the resulting is a vector because of that one there. Okay. All right. So first off, make sure that we can multiply those out. All right. So then now we can ramp this up and say, okay, we can talk about another way of describing basically the same thing we've been talking about with a new thing called a matrix equation. Okay. So I could think of it as, see, like it's a matrix times a vector, but what does that turn into? Some other vector. Okay. So taking a matrix, multiplying by a vector, turns it into another matrix. Okay. Now, before you read this and talk about what it's talking about here, let me look at a different example here and let's dissect what this is saying here. But also kind of what you can see, it's kind of what I was talking about here. Like this is talking about the general m by n, and this is your matrix, whatever it is, and this is your vector here. But again, notice, see how these agree, then matrix multiplication would make sense here. If these don't agree, right? If the number of entries in your rows of your matrix don't agree with your entries in your vector here, then matrix multiplication with a vector wouldn't make sense. Okay. Um, but anyway, what you could do here is what we were just talking about. Like, so let me look at this example here, right? So you could take the corresponding entries, right? And you could even do it like this, like you can do it in chunks, like 6 times -3 would be -18. And then the -2 times 4 would be the -8. And then the 3 times the 1 is the 3. And then you go back and you add them all up, right? So there's your, well, I don't know, you could add them in any order you want, but probably these might be easier to work with first, right? So there's -5 minus the 18 would be -23. Right? And then you could do the same thing here. So adding, all right, well, yeah, adding, but first you got to do the multiplication, 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 right? So here this would be 3, 0, 4, and then go back and add them up. You're going to get 7, right? And there we go. So that's kind of how we were going to look at it. But another way you could look at this is instead of looking at it as row by column, and that way I think is really good to start off with, and it's really going to help later when we get to full-blown matrices. But another way we could look at that is instead of looking at the entries this way, look at them this way, right? So kind of what another way to look at that is you kind of took that -3 and you multiplied by that first column, right? 6, -1. You took the 4, multiplied by that middle one, -2, 0, and then took the 1 and multiplied by the 3, 4, and then add them together, right? So this is just an alternate way of looking at the same thing. But you can see there's your -18, there's the -8, there's the 3, then there's the 3, 0, 4. Okay. But basically, you're going to end up with the same thing, -23, 7, when you go ahead and do it out. Now, here's the point. Why would I do this? Okay. Because another way to look at a matrix times a vector is now what are we talking about? We're talking about a bunch of vectors with scalars added together. So we're right back to what we were just doing in the previous section. We are talking about a linear combination of vectors, right? So instead of this row by column idea, you could think of it as basically a matrix times a vector. It's just a linear combination of vectors where the columns of your matrix are your vectors and the entries of your vector are the scalars that you're using to combine them. And that's what this is saying. All right, so let's get through this mumbo jumbo. So let's say A is an m by n matrix with columns. Now notice these are bold. It's kind of hard to see here, but it's probably easier if you look at your own paper. But these are in bold. So these are, you can think of them as vectors. So column 1, this is a vector, right? It's column 2, this is a vector. Column blah, 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 this would be a vector. So yes, these are all columns in your matrix, but they're also vectors, okay? then your entries in your vector that you're multiplying by would be here. Okay. And again, so the number of columns here or the number of vectors here has to agree with the number of entries in your thing you're multiplying by. And so basically what you're doing is you are now finding some linear combination of these vectors using these entries as the corresponding weights. Okay. And that's basically what this is saying. So it's a linear combination of the columns of A using the entries of, X. That should be X, not B. Oh, the way this was written, this should be X. I will fix that. Sorry, right? But it's and the product of A and X, denoted AX, is a linear combination of A using the corresponding entries of X as weights, not B. The result is B, right? I'll fix that before I send that out. Anyway, okay, so let's check this out. So I guess what I'm saying is how you want to look at it is kind of up to you. Honestly, you should see both ways, right? So what I mean by that is I could take, for example, this one here, I could take this, go like this, and then, take the row by column, row by column, row by column. You could do that, okay? Or you can think of it as basically what you're doing is you're taking this column, negative 4, 6, 0, 5, and this 1, 8, negative 2, 3, and we are going to try to find some combination of these two using these entries as your weights, right? It's really the same thing, right? Because you can see there's basically when you do the 2, negative 4 here and the negative 1, 1, that's the row by column. And then when you do the here and here, that's the next row by column. Here, 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 here. Same thing. It's just a matter of opinion how you want to look at it. But ultimately, what are you going to end up with here? This is basically negative 8 minus 1 would be negative 9, right? 12 minus 8 would be 4. 0 plus 2 is 2. 10 minus 3, 7, right? Mm-hmm. All right. So again, this would be another one would be great to ask him, but you can kind of think of it as 5, 3, 4, negative 1, 3, negative 2. So you can kind of think of it as we are trying to find, this is my matrix, we are trying to find some linear combination of these columns, of these vectors, okay? But you would use the corresponding weights of negative 2, 5, and 0, right? Who is the 0 going with? If you've got 3 entries here, then you have 3 different scalars. We don't have 3 columns here, so this is basically gibberish. This would be undefined. Okay. But that again, you can kind of also see it from like this does not agree with this, right? There's only 2 here, but there's 3 here. Okay. I probably should also mention real quick side note. You could do this on the calculator. Yeah, you don't have to, but just to show you how it works. So like come back to this example here. So like this is one of the nice things about having in the matrix menu. There's a bunch of matrices you could store into here. So like this first one, you could do a 2 by 2, right? And go 3, 2, 4, negative 1. Right. So there's your 3, 2, 4, negative 1, right? And then quit, go back to the matrix menu, but now edit, you could do to another matrix here, right? So in this case, this would be a 2 by 1. And there's your 5, 2, right? Just to show you what I did there. So matrix A, that's the 3, 2, 4, negative 1. And then matrix B is the 5, 2. Okay. And you can literally type it in just like that. So you call up A times, call up B. I know that stupid dots right there. So, but it is indeed 1918, right? And you could do that with all of these, right? I mean, like for example, this one here, you could do this one. You could go back and you could change. This would now be a 2 by 3, right? Where it's 6, negative 2, 3, negative 1, 0, no, and 1. And again, you don't have to, but I like to check, make sure I put it in there right. So we got negative, no, 6, negative 1, negative 2, 0, 3, 4. And then call up B. There's your, oh no, I didn't change B. No. B is a now 3 by 1, right? Which would be negative 3, 4, 1, right? Okay. So now, if we did A times B, right? Sure enough, there's your negative 23. Why is that only? What happened? Did I type that in? I think it's see, this is why you use calculator to check. So what happened? Hold on. Let me make sure I type this in. 6, -1, -2, 0. Oh, see, this I typed in wrong. That should be a that's why it's good to check. Should be a 4. All right, there we go. All right, but anyway, you can see that it definitely does work. And it's probably also worth showing you as well. So like go back to one that doesn't work, right? So if I go to A here, in this case, this is a 2 by 3, 3, 2, 1, 4, -1, 2. And then go to B. This is a 2 by 1, 5, 2. All right. So let me just check. There's a 3, 4, 2, -1, 1, 2. All right, we got that right. And then check B. That is indeed 5, 2. Okay. So now if you did A times B, no. Okay. See, it'll say dimension mismatch. And that's because these don't agree. Okay. So, I mean, you can kind of see that's why, because the dimensions don't line up, right? The rows here and the column here does not match up. Okay. Anyway, so far, what do we got? Just make sure that you can take a matrix and multiply it by a vector. Okay. Also, the bigger point here is when you're taking a matrix and multiplying by a vector, what you can think of it as is you are just trying to find a linear combination of these vectors using these entries as your weights or as your scalars or your constant. Okay. So let's kind of put some all these ideas together. So where this whole thing started was with this linear system. Okay. The point is now we have a bunch of different ways to represent it. You could think of this as a vector equation, like we talked about earlier, or now we can think of it as a matrix equation. Okay. But either way you look at it, we can solve the system of equations. You could solve the vector equation and you could solve the matrix equation all at the same time, right? Because they're all saying the same thing. They're just different ways of saying it, right? So let's do that. All right. So let's say I want to write this system as a vector equation. So as vectors, basically, we're talking about a linear combination of vectors. Okay. So my vectors that I'm using here would be the scalar, the coefficients, right? So think of it as 1, -1, 2. Then here, this is the 2, 4, -3. And then here, this is -1, 2, -5, right? So we are trying to find a linear combination of those three vectors using x1, x2, and x3 as your weights. And we're going to add those up and try to produce the new -3, 12, -22, right? But you can see there's your x1 plus 2x2 minus x3 equals -3. Then the middle one is the negative x1 plus 4x2 plus 2x3 equals 12. And then the last one is the 2x1 minus 3x2 minus 5x3 equals -22. So that would be a vector equation. Okay. But now we can write this as a matrix equation. So basically, what we're doing is we're taking what we were just talking about running it backwards. So now I could think of these vectors here as what I'm trying to find a linear combination of. I could think of it as that is my columns of my matrix A, and I'm going to multiply that by the vector x, which consists of x1, x2, and x3, and that is going to generate the new vector -3, 12, -22, right? But again, you can see that row by column idea, right? So there's your x1, 2x2 minus x3 equals -3. Then -1x1 plus 4x2 plus 2x3 equals 12. And then the 2x1 minus 3x2 minus 5x3 equals -22, right? Or it's basically, again, like I was saying, this column, column, column using x1, x2, and x3 as your weights. Okay. All right. So basically, A is your coefficient matrix. The X is basically your variable vector, really. And then here, this is your constant vector, which we're trying to produce. So basically, A is your coefficients, This X vector is the variable part, and this is what you're trying to ultimately produce or get to. Okay. But anyway, how do I solve this system? Well, you could do some older stuff here. How do I solve this vector equation? How do I solve this? The easiest, most efficient way would be set up an augmented matrix, right? And then row reduce it. But the point is you can solve all three of these the same way. We take our matrix 1, 2, -1, -1, 4, 2, 2, -3, -5. There's your A, and basically augment it. If you want to put that line there, you can with your mate or that vector B, -3, 12, -22, right? And then we row reduce it. Okay. Now I will leave that to you in terms of like if you want to do that by hand, great, right? But hopefully we've done enough of those. We don't need to spend a whole lot of time here doing that. So let me just do this in the calculator just to make the point. So in this case now, if we're row reducing this matrix, this is a 3 by 4. 1, 2, -1, -3, -1, 4, 2, 12, 2, -3, -5, -22. And let me check. All right, so 1, -1, 2, 2, 4, -3, -1, 2, -5, -3, 12, -22. Awesome. All right. So now we can call up our reduced row echelon form of that matrix. All right. So what does that mean? We get basically 1, 0, 0, -2, 0, 1, 0, 1, 0, 0, 1, 3. So what does that mean? You indeed would have a unique solution here. The unique solution would be x1 being -2, x2 being 1, and x3, in fact, being 3. There would be my unique solution. Now, keep in mind, this is a unique solution to all of this, right? So that value of -2 for that value of -2 for x1, that value of 1 for x2, and that value of 3 for x3 not only solves this system, it solves this vector equation, and it even solves this new thing here, this matrix equation, right? It's just that here your x would be that vector -2, 1, 3, right? See, like here, they're kind of corresponding to just x1 by itself, x2 by itself, x3 by itself. Same thing here, x1, x2, x3. But here, I could think of x1, x2, x3 as just one thing. It's one big vector, right? But either way, it's all saying the same thing. Okay. So that's basically the punchline of what this theorem is saying. If A is an n by n matrix with columns, right, and B is, for this matrix equation, AX equals B, this is going to have the same solution set as that vector equation. It's going to have the same solution set as the linear system. You can get it all by setting up this augmented matrix, right, where you take the columns of your matrix A, right, or your coefficients of your system, and augment it with what you're trying to produce, your B. Okay. And basically the punchlines that we got to before, right? This one has a unique solution. So if this has a unique solution, then this is going to have a unique solution. This is going to have a unique solution. This is going to have a unique solution. Now, not in this one, but in other problems, right? If the augmented matrix corresponds to a system with no solution, then the matrix equation would have no solution. The vector equation would have no solution. If there was a dependency, there'd be a dependency for all of these. Okay. And then there's that crazy idea of span. I know there was a lot of questions about that idea of span, but remember, span is basically all of the vectors that you could produce, right? We'll talk more about this, but again, the ultimate point is they're all related to each other. What I mean by that is, this might be jumping the gun. I don't know, but think about this for a minute. This matrix A here, right? This I should point to this one, I guess. This one is A here. Okay. Think about that for a minute. This A here, no matter what this you augment it with, right? That part here is going to be the same. So when you row reduce this, it's always going to be this. If B changes, this would change, which means this would change, but this would not. So what does that mean? That means no matter what B is, when I augment it with, that matrix A, this part is always going to have pivots in every single column. That means you're always going to end up with a unique solution. So if you always end up with a unique solution, that means this system always has an answer. This one will. Or the span of it would be all of R3, right? Since there's always going to be a new unique solution, it doesn't matter what I started with here. I can always get there. If I can always get there, then the span would be everything, right? If this matrix A here, or the coefficient part, right, or the vectors of your vector equation, if that row reduced to something where there were not all pivots, then some vectors I could get to, right? Some I couldn't. The ones I get to would get there infinitely many ways because you'd have a dependency, right? You'd have a consistent but dependent system. But that means there would be other ones I can't get to. So what that means is the span would be some subset of R3, right? So basically the point here is that matrix A, right? If it has all pivot columns like this, you're always going to end up with a unique solution. The span will be all of R3. If that is not all pivot columns, then that means some vectors I can get to infinitely many ways, some I can't, which means the span will be some subset of R3 in this case, right? Let's check this out. Right, so that's kind of foreshadowing where this is going to go. But let's check out some other stuff here to make sure we're with me on the with this idea. So here's my matrix A. If I want to determine if AX equals B has a solution for this, okay? Now again, there's so many different ways you could say this. So think of it as negative x1 plus x2 plus 4x3 equals -2, right? 2x1 plus x2 minus x3 equals 1, blah, 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 blah. Hopefully you can see that linear system there. Also, hopefully you can see what we're talking about there is -2 times this, 1 times the second column, 5 times this. Or in other words, we're talking about a linear combination of these three columns or vectors using these as the corresponding weights, okay? No, that is not what we are talking about here. Oh man, I totally screwed that up. Right? Sorry, this is not X, this is B. We are trying to get to B, right? My bad. Sorry, hold on. So what I'm talking about here is -1, 0, 4, 2, 1, -3. Helps if you read the problem all the way out. We are trying to determine if you can get to this. Now we're not trying to multiply this, sorry, right? So we are trying to multiply by some unknown here, and we are trying to produce this. Right? I totally did that on purpose so that you could follow this rationale. No, I didn't. But anyway, but I think it's worth doing that. Well, that's a good point, right? So here's my matrix A. What I'm asking is, can I multiply by something that would then produce this, right? Or is there some linear combination of these three that will produce this? Okay. The system part that I said at the beginning, that was correct. But basically, since there's see the three here, that means you're talking about three variables, x1, x2, and x3, right? That's what I'm after. I'm after this one vector with three components to it to see if this works. Okay. Or I'm looking for some linear combination of these. Is it possible to have some linear combination of these to produce this? Okay. But anyway, how do I go about doing that? You basically you can set up your augmented matrix, right? So you're taking your -1, 0, 4, 2, 1, -3, -3, -2, -4, and you're going to augment that. Okay, you don't have to put that line there, but I think it's really helpful in this situation with -2, 1, 5, right? And then I'm going to row reduce that. Okay. Again, you can do that by hand if you like, but let me do the calculator so we're not here all day. So again, this would be a 3 by 4, -1, 0, 4, -2, 2, 1, -3, 1, -3, -2, -4, 5. All right, so let's check. -1, 2, -3, 0, 1, -2, 4, -3. Whoops. That's why I go too fast. This should be -4. All right, so 4, -3, -4, -2, 1, 5. Okay, there we go. Now we can row reduce this matrix. Oh, look. See how it ends up with all these crazy decimals here, whatever, right? So you can do math, enter, right? So basically, this is going to row reduce to 1, 0, 0, 0, 1, 0, 0, 0, 1. But notice what I'm doing here. I'm not even looking at that. See, look, there's pivots in all of them. So what that means is you're indeed going to end up with a unique solution. -4/3, 7, 6, and -5, 6. Right? Those would be your that's your unique solution. Or you can think of it as your vector x would be the vector -4/3, 7, 6, -5, 6. Right? That's your actual solution there. So it does have a solution. Okay. One thing you could do just to kind of hopefully you're seeing how all the different things interrelate, just so you see what I'm talking about. So like if I go back to A and basically get rid of the last one here. So let's call it a 3 by 3. But if I do that, I've already got the other one already in there, right? So it's -1, 0, 4, 2, 1, -3, -3, -2, 4, right? So what I'm saying is to check if I go and call then another vector, in this case, the 3 by 1 vector, -4/3, 7, 6, and -5, 6, right? So there's my X. So let's check what is A times B. Sure enough, it produces -2, 1, 5, right? And that's the whole point. If we took A and multiplied by this, what we got for X here, it does indeed produce -2, 1, 5, right? Again, you don't have to, but just to see how it works, right? Another way you could do that is maybe let me think of that first column there, 3, 1. See what I'm doing? This is there's -1, 2, 3, right? It's a lot of typing. I know. Hold on. And then make the next one 3, 1. So let's call this 0, 1, -2. See where I'm going with this, hopefully. And then let's do the third one, 3, 1. Call that 4, -3, -4. Right? See what I'm doing there? So matrix A is basically that first column. Matrix B is the second column, 0, 1, 2. And then matrix C is the third column here, 4, -3, -4. So what I'm saying is if I use these as weights, so -4/3 times A plus 7, 6 times B minus 5, 6 times C, right? So now I'm talking about that linear combination of these. But sure enough, what does it produce? That same -2, 1, 5. Okay. So again, you can see it in all three different ways. You can see it with the reduced row echelon form here as a matrix or even as a vector equation, a linear combination. Okay. But again, here's the bigger punchline. This is where you got to wrap your brain around this. Okay. And again, this would be great. We're being in class because I'd asked you guys, but well, it is what it is here. So let's determine if AX equals B is consistent for all. Well, pause this video and ask yourself that. Do you think this would be true? Do you think for this A here, and no matter what B I pick, not this B, but I pick any other vector in the world, will it always be consistent? Yes or no? And the answer is yes. Okay. Why is that? Again, it's what I was talking about a minute ago. No matter what B I'm trying to get to, right? You're going to take this A here and you're going to augment it with B. Now, if it's a different B, you're going to end up with a different solution, sure. But the point is this part is not going to change. No matter what B I do here, it's going to change this, sure. But the A is never going to change, right? This is always going to row reduce to this. And all of these are pivots. So that means you will always end up with a unique solution. And that's a good point to make. Yes, and but the point there will always be a unique solution as well. Okay. But what does that take that a step farther? What does that mean? That no matter what B I pick here, I can get there, right? And not only get there, but a unique solution. That means that the columns of A would have to span all of Rn, or in this case, R3, right? The N here would be 3, right? So I know span is a weird thing, I know, but think of this: what the span is this is like a Venn diagram. So imagine these are all the vectors in R3, right? Right. I'm just throwing them out there, right? I mean, technically it's a three-dimensional thing. Who cares? But think of this as just a box, right? There's a box, and all of the vectors of R3 are in there. Okay. What I'm saying is, if I took this -1, 2, -3, and 0, 1, -2, and this 4, -3, -4. Is it possible to come up with some number here, some number here, some number here, that the result can generate every single one of these in some way, shape, or form? Yes, that's the point. Because no matter what you set it up with, you will always end up with a unique solution. That means it can get to all of them, right? Basically, we'll see in a second, but If you don't have all pivots, if you have a row of zeros here, then that means you could have a non-zero number here, which means there would be some you can't get to because that would be a no solution, right? I'll show you. All right. But kind of put that all together, right? And this theorem, you will see, man, this is going to grow, right? We're going to be here for a while. When we finally get to, like, I don't know, I think it's like chapter 3 or something like that. There's gonna be like 26 things or some ridiculous. I forgot what the number is, but there's a lot. So this theorem basically says there are so many ways of saying the same thing, just in completely different formats. Okay. So basically, let A be an M by N matrix. The following statements are logically equivalent. What does that mean? That means for a particular A, these statements are all true or all false. So what that means is if one works, they all work. If one doesn't work, none of them work. Okay. It's not sometimes this, sometimes that. No, they're all logically equivalent, right? If one thing happens, you can assume the rest. If one of them doesn't, you can assume none of them work. Right? That's basically what logically equivalent. All right. So what this? Okay. So for each B in Rn, the equation has a solution. So that's what we're talking about here. So if you know that this matrix equation has a solution for any B that you pick, then from there, what does that mean? The columns of A, are some linear combination. You can find some linear combination of columns of A to produce any B. The columns of A would have to span. Every column A is a pivot column, right? All of those are saying the same thing. I think this one is probably your best friend because it kind of leads to the rest, right? If every column is a pivot, right? If they're all pivots, then what that means is it doesn't matter what you, right, these are going to turn out to all be pivots. It doesn't matter what you augment it with, you will always end up with a unique solution. So that means you can get to every vector, whether it's a matrix equation or you think of it as a linear combination, same thing, right? Or the columns of A would span the entire Rn, right? You can get to everybody, basically, right? All right. Let's check this one out. Now, so here is a 4 by 4. Now, I know it leads to directions, right? But don't look at those yet. I mean, like, kind of what you want to do is have some of these thoughts on your own before you just answer the question that's in front of you. All right. So now, first off, realize what is this B here? Does this correspond to a system? Does this correspond to an augmented matrix? Is this a coefficient matrix? I don't know. So if they just straight up tell you, here's a matrix, whoa, don't make any assumptions yet. Okay. So what I mean by that is this, without looking at the context of the problem, this could be, this is your X1, this is your X2, this is your X3, and we're trying to produce this. So you could be talking about three vectors. We're trying to find a linear combination of these three vectors that produces this one, right? Or it's a system with three variables trying to get to here. If that were the case, you are talking about 1, 2, 3, 4 equations. Okay. Or this could be the coefficient matrix itself. So there could be 1, 2, 3, 4 variables, and we're going to use this to produce whatever else. You see that? But I guess what I'm saying is you got to, context clues. What are we talking about? If they just straight up give you the matrix and they don't give you a context, don't assume anything. Okay. Now we read the problem. Okay, it wants you to find the span of the columns of B. So that is now telling me this is not an augmented matrix. This is not talking about three variables producing this. No, no, no. These are all four columns trying to produce blah. Okay, so there's 1, 2, 3, 4 variables indeed. So we are talking about a linear combination of all of these. So that's what they're talking about. The span of columns of B is talking about what is the linear combination of these. Okay. Now, when you, okay, so when you think of span, think of there's this giant list of all of the vectors that can somehow be produced from some linear combination of these. Okay. So, first off, what would be the ultimate goal? Well, since we're talking about four, right? 1, 2, 3, 4, 1, 2, 3, 4. Okay. Then maybe we don't know yet, but maybe we're talking about all of our four. So maybe we can get to some of them, and maybe there's some that we can't get to, or maybe we can get to all of them. I don't know. So it's either we can get to everybody in our four, or we can only get to some of them, and then there would be some that we can't get to, right? Some would produce no solution. I don't know yet. Okay. Well, how we can do that is let's just row reduce B all by itself. Again, you want to do it by hand, go right ahead. Just to save time, let's get to the point. This is a 4 by 4. 1, 3, -2, 2, 0, 1, 1, -5, 2, -3, 7, -2, -8, 2, and -1. Nope. Let's do that. Okay. So 1, 0, 1, -2, 3, 1, 2, -8, -2, 1, -3, 2, 2, -5, 7, -1. So, oops. If you reduce row echelon form that matrix, it produces this. Okay. So when you row reduce this, it turns it into 1, 0, -5, 0, 0, 1, 1, 0, 0, 0, 0, 1, 0, 0, 0, 0. Okay. Again, this would be great if we were in class. What does this mean to me? Well, here's the thing. There are only 1, 2, 3 pivots, right? You do not have a perfect diagonal here. Since you do not have a perfect diagonal, then what is the span of the columns of B? Well, right now, hopefully you realized it's not all of R4. Okay. So we'll talk about it in a minute. I even want to, we'll do this on another sheet of paper. That's why I didn't leave enough room there because it's going to get crazy. Hold on. We'll get to that. Okay. But at least right now, the point here is what I was talking about here. This logical equivalent. Is every column a pivot? No, it is not. So that means the columns are not going to span all of Rn. That means that, like, are you always going to be able to come up with a solution? No, there's going to be some that you can't get to, right? Can you always find some linear combination to produce a given vector? No, there's going to be some you can't get to, right? Or picture wise, think of it as there's some that I can get to, and then there's going to be some that I can get to, right? So these would exist, right? Or you would be consistent for these, but there would be other ones where you would get no solution, right? So picture all of R4. Since you don't have all pivots, I can only get to some of them, right? Some of them, when I augment it with this, is going to produce no solution. Okay. It's a good point to make as well. But the ones you can get to, you will never be able to have a unique solution, right? Because the ones that do indeed produce all entire row of zeros, you're going to have a free variable, right? So it's kind of weird, but I can get to some, but those that I can't get to, I can get to in an infinite number of ways, right? The ones I can't get to, I can't get to. None of them are going to have a unique solution, though. Okay. All right. It wants to know what the actual span is. We'll get there. For right now, all we know is that it's not all of R4. Okay, but there's got to be a way we can describe it as well. We'll get there in a minute. We'll do that on a sheet. Let me show you. But what about this question? What can be said about the solution of this bx equals y? Don't get lost in the lettering here, but this is that same b. We're multiplying some vector, and we're getting to get to here. So what can you say about this solution? Basically, some y, some of these will have a solution. Some y will not have a solution. What can be said about the linear columns of B? Same exact thing, right? I'm not going to rewrite that, but that's the whole point. Okay. So the whole point here is saying that whether this has a solution or not is talking about the same thing about the linear combinations. Okay. So imagine taking, this here and augmenting with this y. Sometimes you're going to end up with the solution, sometimes you won't, right? Or some linear combination of these is going to produce some vectors, some other vectors. There is no linear combination that's going to produce those, right? Okay. So now, how do we actually find this band? Or how can we describe in a way? I mean, like, there's still a bunch of them that we can't get to. There's a bunch that we can't get to. So how could we describe the ones that we can get to, right? Well, it's annoying. It's long, but this is basically what you got to do. Okay. So what is this? This is example 4. 1, 0, 3, -2, 2. Hold on. 0, 1, 1, 1, -5. 1, 2, -3. Oh crap! What happened? 1, 2. Wait. Oh, I have too many. Oh my gosh! Hold on. There's that zero there that should not be there. Hold on. Let's start that over. Silly mistakes. 1, 3, -2, 2, 0, 1, 1, -5. 1, 2, -3, 7. Then -2, -8, 2, -1. Okay. Whew. Right. That's the bad thing about these matrices. It's so hard to copy it down sometimes. Silly mistakes. 1, 0, 1, -2, 3, 1, 2, -8, -2, 1, -3, 2, 2, -5, 7, -1. All right. So now we are trying to produce some other vector, right? So we're going to take this matrix, multiply by my variable, and get to something else. Okay. But I'll try with a number if you're not with me on this. We starting with a matrix and we're trying to find some linear combination of those or some vector to multiply by to produce something else. What we're trying to get to is, can I describe all of the things that I can get to? Well, how do you solve these? You take what you're starting with and you augment it with what you're ending with. But I don't know what I'm ending with. So this is where you have to come up with this arbitrary B1, B2, B3, and B4, right? That's what I'm trying to produce, right? So I'm trying to find some linear combination to get to here. And basically what I want to do is, are there conditions between these four that will enable me to describe which ones I can get to and which ones that I can't, right? Okay. So basically what you got to do is you set it up with an arbitrary vector here, and you got to row reduce it by hand, keeping in mind that these are basically variables, right? Or I should say they're unknown constants, right? But you got to row reduce by hand, basically, is the point, with an arbitrary vector. All right. So the usual stuff, right? This one you got to do by hand now because the calculator won't help you with this variable stuff. So I need a pivot here. Good. 0 underneath it, right? So basically, to get a 1 here, you can multiply by a -1, right? I mean, you could do it in your head, right? But this part, you might want to write it out. I don't know. It's up to you. But basically, I'm going to multiply this by -1. So that's going to be -1, -3, 2, -2, and this is going to be negative B1, right? So that top 1, 3, -2, 2B1 is going to stay put. 0, 1, 1, -5, B2 is going to stay put. But then these are going to come together to make 0, -1, -1, 5. And then here, this is going to be, well, normally you can write it any order you want, B3 minus B1, but it might be nice to keep things in order. So like negative B1 plus B3, right? Just numerical 1, 2, 3 order. That's up to you. Okay. All right. But now I need a 0 here, right? So I can multiply this top row by 2, right? So 2, 6, -4, 4, 2B1. All right, now I can add these together. So there's your 0, -2, -2, 3, and then this would be 2B1 plus B4. All right. All right, so now I got my 1, 0's underneath it. So now my next one, I would love to have a pivot here. Oh, good. It's not only a pivot, but it's already a 1, so I want everybody underneath it. Okay. These you could just straight up already add as is, right? Hopefully you could see that one. So that, let's leave that top 1, 3, -2, 2B1 alone, 0, 1, 1, -5, B2 alone. And then you can just add these together, right? So that's going to give you the 0, 0, 0, 0. And then here you're going to have, again, it doesn't matter, but I just to put in order, negative B1 plus whatever B2 is plus whatever B3 is, right? That's what we'll go here. Okay. And then ideally I'd want a 0 here as well, but I can do that by multiplying this by 2, right? So 0, 2, 2, -10, 2B2. All right. So that last one now is going to be 0, 0, 0, -7, and then 2B1 plus 2B2 plus B4. Mm-hmm. And I don't know if you see it yet, but we're done. Why? I mean, you could keep going. I mean, like, but do keep in mind what the goal here is. If the goal was to actually find the solution to find the X, then yes, you would have to keep going. Okay. But that's not the goal, right? The goal is not to find what the linear combination of these is to produce what vectors. The goal is which vectors can I get to, right? So the goal isn't to get this in reduced row echelon form. The goal isn't to figure out what x1, x2, x3, and x4 are that will produce whatever the original vector was. That's not the goal. The goal is not to find the solution. The goal is to find which vectors would have a solution, okay? And I mean, like you can play around with it and see it, but the thing of it is right here, right? Once you see that, that's the thing that's producing your zero, right? You can also see the pivots here are this one's a pivot, this one's a pivot, and then technically this would be a pivot. So technically, yes, you'd have to flip these and then divide by -7 to produce a 1 there. And then you can keep going to find the actual solution. But I don't care about that. What I care about is right here. What has to be there? If this is any other number other than 0, you're going to end up with no solution, right? So if you had a original matrix here, or well, vector, I guess I should call it, is a matrix, but the original vector, if -b1 plus b2 plus b3 turned out to be 0, then you would have a solution to this. You would have infinitely many of them. But that's the point, right? So in other words, the vectors I can get to have to satisfy this condition. If they don't satisfy this condition, then this would have been a non-zero number. You would have had a bunch of vectors you cannot get to, right? So basically, B1, B2, B3, and B4 can be anything they want as long as they satisfy this condition, which you could leave like that. I mean, that's basically the punchline. Or if it's helpful to you, maybe you could think of it as take one of these and solve for it. So maybe think of B1 as, if you move B2 over, it's going to be negative, move B3 over, it's negative, but then divide by the negative. So then it would have to be B2 plus B3, or you can just move the B1 over. Okay. This might be a better way to look at that. That's up to you. Okay. So I guess basically what I'm saying is you can pick any numbers you want here. Okay. And the sum of these two better be what's sitting there. If the sum of these two is what's sitting here, then you can get to that vector. If the sum of these two is not sitting here, you can't get to that vector. Right? So here, let me check this out. This is the ultimate check to see if we did all that right. Okay. So check this out. Let's go and so you got 1 0 -1 1 0 1 -2 3 1 -2 -2 1 -3 2, and then here this was 2 -5 7 -1, right? Okay, so it's already in there, right? Okay, I guess we should have just done that, but whatever. But you've already got a in there. Okay, so what I'm saying here is, what if I were to take that a and now 4 by 5 augment it with some, so it's blank here. Let's say I would augment it with a random matrix, okay? And maybe try this on your own. Pick some numbers, okay? Let's say I just picked, for boring, 1 2 3, okay? Pick any numbers you want, okay? But hold on. But the point I'm saying here is, in order for this to work, that first entry there better be the sum of B2 and B3. So if this is 1 and this is 2, then this better be 3, right? Okay. Let me call that back up again so you can see, right? So there's my original matrix that we started with, but now I'm augmenting with this new column where I pick numbers, but it does satisfy the property that the first one is the sum of these two. Okay. So now, no. If we indeed row reduce this new one, sure enough, what happens? It's an entire row of zeros. See that bottom? There's a row of zeros, right? Well, here, let me maybe turn it into a fraction so you can see it easier. But you indeed have an entire row of zeros. Okay, that means you would be able to get to that vector that I just randomly picked. You would be able to get there in infinitely many ways with that as your free variable, right? If you were to change that, and let's say this were any other number other than 3, like leave these alone. If I were to pick like 5, see, right now, that last one, the first one here, is not the sum of that, right? So if you did the same thing with this, see, look, you get no solution, right? And that's the point. That would be the actual span, right? The span is infinitely large. There's infinitely number of vectors that I can get to, but they have to satisfy this property. Okay. If they don't satisfy this property, I can't get there. All right. Let me check out some other examples. Gotta think about it. Okay. The heart of it is there. This is a weird example here, but I think it's kind of cool just to make sure that you're paying attention about how these things interrelate. Okay? Don't make this harder than it has to be. Okay. So here, let's say I gave you a vector u, a vector v, and a vector w. First of all, could you show this? Okay, this is just understanding the notation. But basically, what this is saying is 3 of these minus 5 of these minus that better produce the 0 vector. Okay, so we could check that out. So 3 of these use 7, 2, 5 minus 5 of these v's 3, 1, 3 minus w 6, 1, 0. I want to see what this gives me. Well, basically, you could do C7 times 3 is 21 minus 15 minus 6. But 21 minus 15 is 6. 6 minus 6, sure enough, 0. Same thing here. 3 times 2 is 6 minus 5 minus 1, 0. 15 minus 15, basically minus 0, but that's 0. So sure enough, it does indeed produce the 0 vector. Okay, so this particular linear combination of these 3 vectors using those scalars does indeed produce the 0 vector. Okay, not hard. What I think is a little bit more thought-provoking is, could you use this fact up here and no row operations to basically solve this here? This is one of those, if you see it, crazy easy. If you don't see it, it could be a little tricky. Okay. So again, this would be great. We would normally talk about this together and be like, okay, what do you guys think? Right. But hopefully you stare at that long enough, you can see that x1 would have to be 3 and x2 would have to equal -5. Right. The point of this problem is just realizing that, first of all, getting at what that 0 is all about, but also realizing how you can go from a matrix equation, right? A matrix times a vector, producing a vector, to a linear combination of vectors. They're saying the same thing. But the point here is, see this 7, 2, 5? Oh, that's my u, right? See the 3, 1, 3? That's this, okay? Or I could think of it as, this is basically saying there's some number times that 7, 2, 5, plus there's some number times 3, 1, 3. Sorry, I didn't there. But that would produce this 6, 1, 0, right? But you basically have that 3 of these minus 5 of these minus w would get you to 0. So I could move this over and I could think of this as x1 times the u for laziness, x2 times the v minus w does indeed produce 0. What does that mean? X1 had to have been 3 and x2 had to have been -5, right? So it's kind of a weird question, but it's just realizing how you can interrelate back and forth between a vector and the matrix deal. Right? All right. A couple other things here for you. Just kind of some thought provoking, right? So, I mean, like, so I guess what I'm saying is like this stuff here that we talked about so far, that's your, you know, plug and chug, how the stuff works. This is more of a, okay, can we think through these logically, you know, getting a little deeper. All right, so let's check this out. Put a set of 3 vectors in R4, span all of R4. Explain. And then ramp it up. Okay. So you got a set of 3 vectors in R4. So first of all, what does that mean? That means you have 3 vectors. Well, let's just do it. In R4, meaning that you 1, 2, 3, 4. You have one vector with 4 components. You have another vector, 1, 2, 3, 4 components. And you have another vector, 1, 2, 3, 4 components. Right? So the question is, could these 3 vectors in R4, could you span all of R4? So could you generate everybody in R4? And if you haven't thought about it yet, the answer would be no, you cannot, right? Why not? Well, think about it. If I'm trying to find some linear combination of these 3 to produce basically anything I want in R4, you would have to have 4 pivots. You can't have 4 pivots, right? You could have 1, 2, 3, but you would never be able to produce that 4th one. Okay. Now, do keep in mind that there could be 3 pivots. There could be 2. There could only be 1. Okay. but you can't have all four. That's basically the point. You can't have all four pivots. Since you can't have all four pivots, that means there's going to be some things that when you augment this with, is going to generate no solution, right? That's basically the point. Right. So it's, well, I guess I should say not all four pivots. Okay. And that's basically the point here. Could what about n vectors in Rm where n is less than m? So if you have less vectors than you have entries, no way, right? Because basically, however many entries there are, you would need that many pivots in order to get there, right? So if you had eight, you're trying to get to R8, you would need at least 8 of them, right? If you had less than that, you wouldn't be able to get there. What about the other way, though? What if you had 4 vectors in R3? Could that span all of R3? Okay. So now we are talking about 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. Okay. So think of it as we are now talking about 1, 2, 3, 4 vectors with 3 entries. Could that span all of R3? Yes. But do keep in mind, does it have to? No. It could, though, right? So it is possible to end up with 3 pivots, right? So if you had 3 pivots, right, if you had 3 of them, then you could get to anything. Okay. Now, it's also possible that maybe you don't have 3 pivots. You could have less than that. Okay. But the point here is you could have all 3. Here, you could not have all 4. No matter what these are, you can't. Okay. These here, depending on what they are, maybe there's less than 3, which means then you wouldn't be able to span them all of R3. But it's potentially possible to get to all of R3. Right. That's the idea. Okay. Another one here. Suppose A is a 3 by 3 matrix and B is an R3. Suppose AX equals B has a unique solution. And what is the span of the columns of A? There's a lot of back and forth mumbo jumbo here, but once you get used to it, hopefully that's not that hard. So take an educated guess what you think the span would be. But if what this is basically saying, you got a 3 by 3. B is some random vector in R3. And let's say this particular thing has a unique solution. Okay. If it has a unique solution, A is a 3 by 3, that means you got a 3 by 3. But no matter what I augment that with, I know this is really crappy notation, but I think this is you with me on this, right? So imagine here's your A, and you augment that with whatever B is. Now B has got 3 entries. I'm just lazy. I just wrote B instead of all 3 of them. Okay. But the point is, if this has a unique solution, then what does that mean? There would have to be 3 pivots. If you've got 3 pivots, then that means it doesn't matter what you augment it with. You will always end up with a unique solution. So that means you can generate any B you want, no matter what it is. So what would the span of it be? All of R3, right? It wouldn't be a subset of R3. Okay. All right. Suppose AX equals B has infinitely many solutions now. So a different deal here, but it's the same thing. You got a 3 by 3. Okay. But let's say it turned out that it had infinitely many solutions. Now, if you had infinitely many solutions, then what does that mean? That means you had to have had a row of zeros for that particular B. And maybe there's only 1 pivot, or maybe there's 2, but there can't be all 3, right? Because of the infinitely many. Okay. So then what does that mean? That means there had to have been other vectors that you couldn't get to because that would have produced a no solution. So what would the span of the columns of A be? It would have to be some subset of R3. You couldn't generate all of them. So think, again, this is like a Venn diagram. Here's R3. I can get to everybody I want in this one. Okay. In this one here, there would be some that I can get to and some that I can't, right? So this was like the span, right? So visualize all of R3. If there's a possibility of some you get to and they get to them infinitely many ways, that means there would have to be other ones I can't get to, right? All right. So seeing it's all kind of the same stuff in different ways. So the matrix equation, the vector equation, all that good stuff, and then even how that relates to the span.